Hello, and welcome to the Turing-Roche Demystifying video series. My name is Vicky Helen, and I'm the Community Manager for the Turing-Roche Partnership, which is a 5-year collaboration between the Alan Turing Institute, the UK's National Institute for Data Science and AI, and Roche, the global pharmaceutical company. Our partnership is aiming to generate insights into disease, patient, and outcome heterogeneity using advanced analytics to improve clinical care. This video series aims to demystify concepts relevant to the partnership's research aims. For this video, I'm delighted to welcome Rohan Chakraborty, Senior Research Associate for the partnership, who will be demystifying Bayesian estimation for us.
Hi everyone, I am Rohan. I am a Senior Research Associate at the Roche Turing Partnership at the Alan Turing Institute. Today we shall be demystifying a couple of preliminary concepts on Bayesian inference, particularly MLE and MAP, maximum likelihood estimate and maximum a posteriori estimate, by drawing parallels with the well-known Bayesian rules of conditional probability. We shall do so by starting off with a fairly simple numerical example on conditional probability and gradually draw connections with concepts of MLE and MAP as we continue to solve this numerical problem. Hopefully, at the end of these 5 minutes, this will lead us naturally to a working formula connecting MLE and MAP to the classic Bayesian rule of conditional probability that we all know and love. So let us crack on. I will first read the problem statement. Tom works as a cashier for a currency exchange company at Heathrow, selling British pounds and euros. The company segments their customers into 3 main world regions: Commonwealth, Europe, rest of the world. According to the company's statistics, 30% of the customers coming from a Commonwealth country buy euros, 90% of the European customers buy British pounds, and 50% of the customers from other parts of the world buy euros. So the question is, if a new client buys pounds, what is the most likely region of the customer? This is a fairly straightforward question for anyone who has already studied conditional probability. But it will be interesting to link this to the concept of maximum likelihood estimate, MLE. So we define 2 variables, X being the geographical region, Commonwealth, Europe, and rest of the world, and Z being the currency, British pound or euro. Now, the conditional probability of Z given X can be directly taken from the problem statement itself, and we create this nice table here with values that we have taken directly from the statement. Now, what we say is that our estimate, the probability estimate is 0.9, since that's the maximum probability, and so which would mean that we are saying that the most likely region of the customer is then X equals 2, which is Europe. Now, the thing to note here is that what we were asked to find out is the most likely region of the customer, given that the client buys pounds. So this means that what we were asked to find out is actually probability of X given Z, X being the region, Z being the currency. But since we did not have enough information to find out probability X given Z, the best estimate of that we could do from the values we had is actually probability Z given X. So this means, given the information we have, that's our maximum likelihood estimate. So hence, probability of Z given X being a proxy of probability X given Z is the maximum likelihood estimate. Next, we are provided a bit of extra information, which is also called the prior information. Here it is the marginal probability of X, which is how many people come from which geographical region, and that will help us to proceed towards a better estimate, which is the posterior estimate, or in this case the MAP, the maximum a posteriori estimate. So the extra information is, suppose that the sales department gives us new information about the customers of the company. We know that 10% of the customers come from a Commonwealth country, 30% from Europe, and 60% from rest of the world. Write down the joint distribution that describes the region and the currency bought by a customer. So from this information, we write down the marginal probability X, and multiplying that with our previous probability Z given X, we end up with the joint distribution, probability Z and X. Why is this important? If we look at the equation on the right, which is just the conditional probability equation, we see that it is the numerator of the equation, the joint distribution. So unlike before, where we had to be satisfied with probability Z given X being a proxy estimate MLE of what we actually want to find, which is probability X given Z, now we are slightly inching closer to the actual value. But we are still lacking the denominator, which is probability of Z, which we shall get in the next part. So how do we find out the evidence or probability of Z? If we directly look at the last table in this slide, we see that what we are trying to find out is probability of X given Z equals 1, because we know that the person has bought pounds, so Z equals 1, and given that which geographical region they come from. So the evidence here is probability Z equals 1, and you can find that just by adding up the columns. So given Z equals 1, then adding up, we get a probability of 0.64. And we can normalize each of the rows by those added values, and it all adds up to 1. That's how we get the last table here, which is basically the first entry is 0.07 divided by 0.64 from the previous table. And we can readily see that now our sort of posterior estimate that is that the person is probably from X equals 3, that is from the rest of the world. Whereas the MLE, the maximum likelihood estimate, or sort of the naive estimate, was they are probably from Europe. Why has this changed? So two things to note here. This has changed because we now know that most people are from the rest of the world. That is, that prior information, which is probability X equals 3 is 0.6, much larger than the other two, changed our estimate, made it more accurate, and we sort of changed our belief or decision in this case. The other thing to note, the second thing, is that this normalization, that is division by 0.64 in this case, doesn't change the posterior estimate. Even before the normalization, from the second table here in this slide, we see that the maximum probability given Z equals 1 is for X equals 3.3. So, and that remains maximum in the last table, obviously, because all the entries are divided by the same value, 0.64, in the first row. That is why the evidence in the MAP-MLE relation in most Bayesian estimate, Bayesian inference text is also called the constant, because it doesn't really change our estimate in this case. So this is how it ties back to the original conditional probability theorem. And this numerical example was just demystifying the concepts of Map and Emily, how they're nothing but interesting ideas originating from conditional probability. Hope this helps. Thank you.
Thank you so much, Rohan, for that video. We hope you found it informative and helpful. You can check out more videos at our YouTube channel, and please follow the link on the slide to find out more about the partnership and how you can engage with us through things like our Slack workspace, newsletter, knowledge share events, and more.